Given any time t in hours, our function c of t tells us how much drug is left in the bloodstream. If we want to know the amount of the drug in the bloodstream after 4 hours, all we have to do is sub in t equal to 4 into our function. In other words, we replace each of the t's with a 4. This gives us minus 4 to the power of 3 plus 4.5 times 4 squared plus 54 times 4. Calculating these gives us minus 64 plus 72 plus 216. Performing this calculation gives us 224 units, which is precisely the answer we wanted to obtain. The top row of our table is labelled with the time t in hours. The bottom row is labelled with our function c of t. To fill in the entries in the second row, all we have to do is take the relevant t value and sub it into our function. In part A, we subbed in t equal to 4 and got an answer of 224. This is the reason that we have a 224 underneath our 4. Completing the table simply requires us to sub in the other t values in a similar way. Our function is that c of t is equal to minus t to the power of 3 plus 4.5 t squared plus 54t. Our first blank is underneath t is equal to 2. To find this, we will sub in t equal to 2 into our formula. This gives us minus 2 to the power of 3 plus 4.5 times 2 squared plus 54 times 2. Doing this in our calculator gives us an answer of 118. So this is what we'll write into the box underneath the 2. The next blank is under t is equal to 3, so here let's sub in t equal to 3. This gives us minus 3 to the power of 3 plus 4.5 times 3 squared plus 54 times 3. Doing this in our calculator gives us 175.5, so we'll write this in underneath the 3. Filling in the rest of the blanks will work in a similar way. We just need to sub in t equal to 5, 6, 7, 8 and 9 into our function. Subbing in t equal to 5 gives us an answer of 257.5. Subbing in t equal to 6 gives us an answer of 270. Subbing in t equal to 7 gives us 255.5. Subbing in t equal to 8 gives us 208. And subbing in t equal to 9 gives us 121.5. In part B, we filled out a table. The data here told us the number of units of the drug left in the bloodstream, C of t, at various times t. For example, when t was 0 hours, we had 0 units. When t was 1 hour, we had 57.5 units. And when t was 2 hours, we had 118 units. We have similar information for t is equal to 3, 4, 5, 6, 7, 8 and 9. This data forms 10 pairs. Each of these pairs can be plotted as a point on our graph to give us an idea of the shape of our function. In our graph, the horizontal t-axis represents the time in hours. This corresponds to the first row of our table. The vertical axis is labelled with C of t, the amount of the drug in units. This corresponds to the second row in our table. So let's plot our points. In our first pair, we have t is equal to 0 and C of t is equal to 0. Going to a value of 0 on both axes gives us a point right here. In the second pair, we have t equal to 1 and C of t equal to 57.5. Here, we'll go across to 1 on our t-axis and up to 57.5 on our C of t-axis. This gives us a point right here. In our next pair, t is equal to 2 and C of t is equal to 118. So we go to 2 on our horizontal t-axis and up to 118 on the vertical C of t-axis. This gives us a point over here. We can perform a similar procedure for the rest of the remaining points. The data in our table gave us 10 points to plot. This gives us a rough structure of the function. To finish our graph, we should join these reference points with a smooth curve. In our graph, the horizontal axis represents the time t in hours, and the vertical axis represents C of t, the amount of the drug left in the bloodstream in units. In part I, we are provided with a time, 3.5 hours. The horizontal axis represents time, and 3.5 is right here. Let's draw up a vertical line and see where this intersects our graph. To find the amount of the drug in the bloodstream, we just need to read off the vertical C of t value for this point. We can do this by drawing a horizontal line across. We get a value of 200. This is our estimation for the amount of the drug in the bloodstream after 3.5 hours. In part II, we are provided with the amount of the drug in the bloodstream. It's 100 units. Our vertical axis represents the amount in units, and 100 units would be right here. Let's draw a horizontal line across to see where this intersects our graph. To find the time it takes for there to be 100 units of the drug in the bloodstream, we should drop a vertical line down and read off the value from our time axis. The value here is approximately 1.7. So our answer is 1.7 hours. We need to find the rate at which the drug amount is changing. A key point to keep in mind here is that the rate of change is obtained by differentiating our function. At its core, this is what differentiating does. It tells us the rate of change. So whenever we see the phrase rate of change in a question, alarm bells should go off and we should think about differentiation. Our function is c of t is equal to minus t to the power of 3 plus 4.5t squared plus 54t. To find our rate of change, we just need to differentiate this. Whenever we're adding or subtracting terms, we can differentiate each term individually. So we can tackle the three components here separately. First, let's focus on the minus t to the power of 3. To differentiate this, we can use our rule for differentiating powers. We multiply down by the power, then reduce the power by 1. Here, the power is 3, so we'll multiply down by 3, and then we'll reduce the power from 3 to 2. So we get minus 3 t to the power of 2. We can use the same strategy to differentiate the 4.5t squared. Here, the power is 2, so we'll multiply down by 2, and then reduce the power from 2 to 1. 4.5 times 2 gives us 9, and t to the 1 can just be written as t, so this gives us 9t. Finally, let's tackle the 54t. There's a useful fact which says that for any constant k, k times t simply differentiates to k. In other words, if you have a number being multiplied by t, it just differentiates to the number. Applying that here, 54t will just differentiate to 54. So our final answer here is that the rate of change of our function, c dash of t, is equal to minus 3t squared plus 9t plus 54. In part EI, we found the derivative of our function, c dash of t is equal to minus 3t squared plus 9t plus 54. This derivative represents the rate of change of our function. We're asked to find the rate of change after 4 hours. Since t represents time in hours, all we'll have to do here is sub in t equal to 4 into our derivative function. This gives us minus 3 times 4 squared plus 9 times 4 plus 54. This simplifies to minus 48 plus 36 plus 54. Performing this calculation gives us our final answer of 42 units per hour. We need to find the maximum amount of the drug in the bloodstream. To find the minimum or maximum of a function, we can follow these steps. First, we differentiate the function. Then we'll set the derivative equal to 0 and solve. And finally, we'll sub back into the original function. The original function we were given was c of t is equal to minus t to the power of 3 plus 4.5t squared plus 54t. The first step would be to differentiate this function, but this is something we already did in part EI. Here, we found that the derivative, c dash of t, is equal to minus 3t squared plus 9t plus 54. The second step is to create an equation by setting this derivative equal to 0. Our equation involves a t squared term, a t term, and a number term. This is referred to as a quadratic equation, and it can be solved using the quadratic formula. This tells us how to find the roots of a quadratic ax squared plus bx plus c is equal to 0. This is similar to the form our equation is in, but we should note that we have t playing the role of the x. To use our formula, we'll first need to identify the values of a, b and c. A will be the number in front of the t squared, which here is minus 3. B is the number in front of the t, and here b is equal to 9. C is the number all by itself, so here c is equal to 54. Let's sub these values into our formula. We can simplify things a bit here. 9 squared is equal to 81. Minus 4 times minus 3 times 54 is plus 648. And 2 times minus 3 is minus 6. Under the square root, 81 plus 648 gives us 729. As it turns out, if we type root 729 into our calculator, we get a nice whole number. It's 27. From here, we need to deal with the plus minus sign. This symbol means that we need to split into two cases. In the first, we replace the symbol with a plus, and in the second, we replace this symbol with a minus. In our first case, minus 9 plus 27 all over minus 6 comes out as minus 3. In the second case, minus 9 minus 27 all over minus 6 gives us plus 6. So we've ended up with two values of t. But remember, t represents a time in hours. In this context, a negative value of t doesn't really make sense. So we can rule out the t equals minus 3 and focus on the t equal to 6 moving forward. The interpretation here is that the drug amount will be maximised after 6 hours. However, we weren't asked to find the time when the drug amount is maximised. We wanted to find the actual amount of the drug at this time. To find this, all we have to do is sub in this t equal to 6 back into our original function c of t. C of t is equal to minus t to the 3 plus 4.5t squared plus 54t. To sub in t equal to 6, we just replace each of the t's with 6. This gives us minus 6 to the power of 3 plus 4.5 times 6 squared plus 54 times 6. This simplifies to minus 216 plus 162 plus 324. Performing this calculation gives us our final answer of 270 units. We need to show that the drug amount is decreasing after 7 hours. A key point to keep in mind here is the following. A positive rate of change means that the function is increasing, whereas a negative rate of change means that the function is decreasing. So to demonstrate that the function is decreasing, we just need to show that the rate of change is negative. Well, we've seen before that our derivative tells us the rate of change. And in part EI, we found our derivative. C dash of t is equal to minus 3t squared plus 9t plus 54. We are asked to consider a timing of 7 hours after the drug is taken. To find the rate of change at this time, all we have to do is sub in t equal to 7 into our derivative. This gives us minus 3 times 7 squared plus 9 times 7 plus 54. This simplifies to minus 147 plus 63 plus 54. Doing this calculation gives us an answer of minus 30 units per hour. The crucial thing to note here is that this rate of change is negative. So at t equal to 7, the rate of change is negative. Hence we can conclude that the drug amount is decreasing at this time.